Assalamu alaikum warahmatullah. Today I'm going to explain about our experiment, which is simple DC motor. This experiment has been done by group 4 for the course of SEEE 2523 section 9. So first I'm going to introduce our group members. So voiceover is by me, Amjad Tariq, experiment recording by Mahmoud Abdul Wasi, and slide making was by Umar Amgad, and lastly video editing by Ahmed Al-Sayed. Okay, so in this video we are going to explain about what is DC motor, express the basics of operation of the electromagnetic theory behind it, and lastly showcase the experiment. Okay, so this is the simple DC motor, which consists of three parts: current source, magnetic field, and free rotating wire here, as shown in this figure, and it's used to convert electrical energy to mechanical energy plus heat. Okay, in electromagnetic theory we can divide the application in terms of field to three applications, which is electrostatic field, magnetic field, and electromagnetic field. In our experiment we'll be using the magnetostatic field because we have here a charge moving in external magnetic field P. As you can see here from this equation, the magnetic force is equal to charge multiplied its velocity cross product, the magnetic field. A magnetic field here can exert force only on a moving charge. By definition of current here, we can conclude this equation. So the magnetic force F depends on three main things: length of the wire, how strong the magnetic field is, and lastly how much current there in the wire. And we should note that DL and B must be not parallel, it can't be parallel. So moving to the next slide, which is about torque. So the torque, or the mechanical moment of force on the loop, we can define it as the product of the moment R multiplied by the F, which is force. And as you can see in the graph, we have the F vector here and the R, which is the moment R. Okay, moving to planar and side views. In this planar and side view, AB and CD here are parallel, so they contribute 0 to the force. We can integrate then AD and BC, okay, in the previous equation. So this is the force that keeps the coil rotating. Moving to the magnetization in material. In atomic scale, without an external B field applied to the material, the sum of the M's is 0 due to the random orientation, as you can see here in the left figure. For the right figure, when external B field is applied, the magnetic moment of the electrons align themselves together, as you can see. So the net magnetic moment here is not 0. We have two applications, converters and fans. We have chosen this one because this DC motor are very useful when we have a low and adjustable speed is required, such as these two examples. However, in industry they are used in dynamic braking and reversing application. So that's all for explaining our part in the DC motor. Now we'll move to the part of experiment video. Thank you.